Today I'll be presenting about work that I've done mainly last year about Bayesian inference and global sensitivity analysis for ambient solar wind prediction. And this is work with different collaborators. Pete Riley, he's at Predictive Science Inc. here in San Diego. It's a solar physics research company. Enrico Camporale, that I guess is now in London. And we have Boris Kramer, who's my PhD advisor here at UC San Diego. So I'm going to start simple. What is the solar wind? We'll start with definitions. So it's the continuous flow of charged particles that are able to escape the sun's gravitational pull. And this happens due to very, very high heating in the sun's corona. So it reaches about 2 million degrees Fahrenheit. And this talk is going to focus on the ambient solar wind. So this is essentially the long-lived large-scale structure in the solar wind. So it excludes any transient events, such as solar flares and coronal mass ejections. So here on the left, you can see a cartoon how the solar wind interacts with Earth's magnetic field and the magnetosphere. And then yesterday we had a solar eclipse. So I added a photo that my friend sent me from Mazatlan, Mexico, where they had a full coverage, and you can see how it became dark. So during a solar eclipse, you can see the sun's corona. Okay. All right. So our goal is to predict the ambient solar wind, and we have models to do this. But these models have some uncertainty. So the uncertainty can stem from many things, such as physics approximations, numerical errors. You can also have measurement error. You have parametric uncertainty, fitting parameters, other things. But today we're going to focus on parametric uncertainty. And this stems because some parameters are sort of fitting parameters. So either they come from reduced physics approximations or from empirical relations. And we want to understand how do uncertainties in our parameter affect our predictions. So we want to reduce and quantify the uncertainty. And we have here an uncertainty quantification framework. So this is pretty standard, but I'll walk you through it. You start off with your model and available data. And then you identify the uncertain parameters in your model. And you're going to assume some prior assumptions. So we're treating, this is in the Bayesian framework, so we're treating these parameters as random variables. So they have some distribution associated with them. And in this work, we use uniform priors, so non-informative priors. And then we move into phase one, where we do global sensitivity analysis. And here we're trying to understand which parameters influence our predictions the most. So what are the biggest drivers of our predictions? And then parameters that are non-influential will set as their nominal value. So that will give us a parametric dimensionality reduction, where in phase two, we will only learn the posterior distribution of the influential parameters. And this is quite computationally expensive, so that this is why we do this two-phase approach. And then once we have our posterior, we can generate ensembles, and that's when we'll be able to quantify and reduce our uncertainty in our prediction. Okay, so what are the main questions that we're trying to answer with this uncertainty quantification framework? Well, first, this is answered in phase one. What are the most influential parameters in a given ambient solar wind model? And we're going to answer this by computing the global sensitivity indices. The second question is, how do the posterior densities of the influential parameters change over time? And by analyzing this, we will understand if there is a clear trend in the posterior evolution. And then lastly, we want to check if the model is robust to the choice of its parameters, and is it reliable enough for real-time operational forecasting purposes. So here on the right, you see a screenshot I took yesterday from the NOAA Space Weather Prediction Center. And this is one of the ambient solar wind models that they use for operational forecasting, where they couple the Wang-Sheeley-Arge model with Enlil. And here you see the plasma density and the radial velocity for tomorrow. So this is a real-time forecasting models that they use. And so which models are we going to look at in this study? There's many out there, but we're going to use some of the models that are most commonly used in literature. So we have, for the coronal domain, we're looking at the potential field source surface model. And this is essentially a reduced physics approximation. So we look at the Ampere equation and we assume that the current is negligible, and then we actually and we also assume that it's static, and then you end up with a Laplace equation. So you're solving for the magnetic potential in the coronal domain, and this is a three-dimensional model. And then we assume for our boundary conditions that the magnetic field, the radial magnetic field on the surface of the sun, the photosphere, is given to us by these Gauss synoptic maps. And at the coronal heliospheric boundary, we're going to assume that the magnetic field is purely radial. And then at this interface, we're going to use the Wang-Sheeley-Arge model. So if you remember from the previous slide, this is used in operational settings. And this is an empirical model. And from the potential field source surface model, we can actually get the radial velocity at this interface. And then we're going to propagate that radial velocity profile in the heliospheric domain using the Hux model. And this is also a reduced physics model where it's based on the momentum equation, and it's a hydrodynamic approximation of the flow. And so here are this is used for our boundary condition, which is inputted into our PFSS model, moved into WSA to Hux, and then we can actually compare our radial velocity predictions near Earth, specifically at the L1 trajectory, with ACE in situ measurements. So just to reiterate, here are the equations for the three models, and as you can see, the WSA model is an empirical relation between the distance to a coronal hole and also the expansion factor of the magnetic field lines. And so what are the uncertain parameters in this model chain? We identified 11. Most of them come from the WSA model because we have some fitting parameters. And then for the PFSS model, the boundary between the coronal and the heliospheric domain is uncertain because we assume that it's spherical, and in reality it's not spherical, and this can also change between Carrington rotations. All right, so we move into phase one, and here we look at global sensitivity analysis, and the goal is to compute Sobel indices. So these are scalar indices, and the goal is to understand how does uncertainty in my input contribute to variance of my output. So for first order indices, what you do is you vary one parameter and you see how does this contribute to the variance of my output. For second order indices, you vary two parameters simultaneously and you keep the others fixed and you see how does that contribute to the total variance. And then for the total order index, you sum up all these different indices that are related to that xi parameter. So a little bit about notation. F here is our quantity of interest. X is our uncertain parameters. So just again, a little bit of intuition. If the total order index is close to 0, that means that your parameter is not influential. So this is how we can do that screening to understand which parameters are influential. And we approximate all of these integrals using a Monte Carlo approach. So here are the numerical results. We compute the total order indexes for 3 Carrington rotations, and they're equally spaced, 5 Carrington rotations from one another. And this is during solar cycle 23 in 2007 during solar minimum, where our model was fairly accurate. And our quantity of interest is our root mean squared error between the model predictions and ACE observations at ACE trajectory. And what we see is that the 5 most influential parameters have the same ordering between different time periods. So that tells us that we could probably interpolate these results in between these time periods. And the 5 most influential parameters are WSA parameters. So now we're going to move into phase 2, where we will learn the posterior distribution of these influential parameters. And by Bayes' rule, we know that the posterior, which is the probability of the influential parameters given the data, is proportional to the likelihood times the prior. And for priors, we assume uniform priors, as we did for the global sensitivity analysis, and the ranges for the uniform priors are given from literature review. So we check what are the minimum and maximum values that people used in literature with these models. And in order to formulate the likelihood, we make one more assumption that our data, our ACE observations, the radial velocity observations, and our model predictions are related by some Gaussian noise. So we assume that our model is unbiased, and the standard deviation, again, is given to us by the literature. And so now that we have our likelihood, we use a Markov chain Monte Carlo algorithm to generate the posterior densities. And in particular, we use the affine invariant ensemble sampler. So this is an unbiased estimator. So at the limit of infinitely many samples will converge to the true posterior. So here are our numerical results. We see, we looked at 10 consecutive Carrington rotations during solar minimum in solar cycle 23. And what we see is that our parameters in evolution in time changes drastically from one Carrington rotation to the next. And we suspect this has to do with the following reasons. So one of them is that our model chain, even though it's used commonly in literature because it's computationally attractive, it does have some limitations because we have some empirical relations and also reduced physics approximations. And so we think these parameters are trying to overcompensate the intrinsic and hardwired limitations of these models. And then we also suspect this is due to the fact that the Wang-Sheeley-Arge model is over-parameterized. So in future work, we would like to reformulate this model where we will balance between parsimony and accuracy so we don't overfit with the number of parameters that we have in this empirical relation. But from these posteriors that we generated, we can actually take these samples and have an ensemble prediction. And what you can see is that prior to computing the posteriors, if we sampled from the priors, which were uniform distributions, we get a very large credible interval, so highly uncertain predictions. And our median is not very accurate. So black is the ACE observations. And after the UQ framework, we are able to not only improve the accuracy of our median, but also significantly reduce the uncertainty in our predictions. So to conclude, we proposed here this UQ framework for ambient solar wind predictions. We performed in phase 1 global sensitivity analysis, and we saw that the 5 most influential parameters are all from the WSA model. And then we learned the posterior distribution of these influential parameters using MCMC. And we saw that they change greatly in time, which motivates the investigation of the forecasting capability of this model chain. And lastly, we were able to quantify and reduce the parametric uncertainties using these posterior distributions. So all of this code is available on my GitHub repository, and this is a QR code for our paper that we published in the Space Weather Journal. Thank you very much.